Welcome to this video on hydrogen-based reduction of iron powder, a sustainable way to make steel. Today, we'll explore how this innovative process can help us move towards cleaner steel production. Iron powder is gaining recognition as a promising alternative to fossil fuels because it's abundant and has high energy content. By burning iron powder, we can generate energy through oxidation. After that, we use hydrogen to reduce the oxidized powder back into reusable iron, creating a circular and renewable energy supply. To provide some context, let's understand how hydrogen-based direct reduction works. It's a cleaner way to produce steel that uses hydrogen instead of coal. This process could potentially replace coal-based blast furnaces and drastically reduce carbon emissions. In this study, we examine how deeply oxidizing the iron powder affects the reduction process and whether it can lead to a cleaner steelmaking approach. To understand how deeply oxidizing the iron powder affects its reduction, they use two types of iron powders, part ox and full ox. Part ox is partially oxidized to contain 50 magnetite and 50 hematite. However, full ox is fully oxidized to 100 hematite by heating part ox to 900 degrees Celsius. First, they used thermogravimetric analysis. We heated both part ox and full ox powders to 400 degrees Celsius, 450 degrees Celsius, and 500 degrees Celsius in a pure hydrogen environment. By measuring weight changes during heating, they could see how quickly each powder reduced. Second, they used high-energy X-ray diffraction to watch the phase transformations of the powders at 500 degrees Celsius. This technique allowed them to see the reduction of hematite to magnetite and magnetite to pure iron step by step. Visualize surface morphology and cross-sectional features of the powders during reduction. Finally, they used electron backscatter diffraction to identify the different phases and grain orientations in the powders. Results from the reduction process provided key insights into how deeply oxidizing iron powder affects the reduction kinetics. The microstructural analysis revealed that part ox and full ox powders reduce differently. Part ox had uneven porosity due to simultaneous reduction of magnetite and hematite. On the other hand, full ox showed even porosity because it was fully oxidized to hematite. They found that each phase followed a distinct reduction models. This graph illustrates how fast part ox and full ox powders reduce at different temperatures. The microstructural analysis revealed significant differences between part ox and full ox powders during reduction. Part ox due to the simultaneous reduction of magnetite and hematite, part ox showed uneven porosity. Long porous regions align with the original hematite grains. On the other hand, full ox, which was fully oxidized to hematite, displayed even porosity. The deep pre-oxidation treatment created a porous hematite network that facilitated reduction. This figure 1 shows part ox and full ox before reduction. Here, we can see how phases change during reduction in figure 3. This cross-section illustrates part ox and full ox after reduction with figure 4. In conclusion, deep pre-oxidation of the iron powder accelerates the reduction process when gas diffusion is limited, leading to a uniform, porous structure. This finding makes hydrogen reduction steelmaking a promising method for sustainable steel production and energy generation. Images of surface analysis show how the surfaces of part ox and full ox look after reduction. If you're interested in learning more, you can download the full research paper using the link in the description. See you in our next video.